Hello and welcome to this presentation on thyristor family device SCR. In this presentation, we'll cover up SCR. Myself, Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology, Bhandari, Thane. So this is the first unit of thyristor family device of the subject Basic Power Electronics in MSBT syllabus. So this unit is allocated 18 marks out of 70 and 12 hours of lectures. The course outcome of first unit is to identify power electronic devices in circuits, and unit outcomes after completion of this unit outcomes expected of the learner is first one to explain with sketches the working principle of the given type of thyristor, second interpret VI characteristics of the given power electronic device, thirdly calculate latching current and holding current for the given type of SCR, fourth select a relevant triggering device for the given circuit with justification, and fifth identify various power electronic devices along with their specification, describe with sketches the procedure to troubleshoot the simple type of thyristor circuit. So here we are dealing with the SCR in this presentation with respect to construction, with respect to operating principle, and with two transistor analogy we will study VI characteristics, and in that we will see the latching current and holding current, and finally the applications of SCR. So in this diagram here we have many pictures which shows the first picture here shows the layered structure of the silicon control rectifier. So SCR is silicon control rectifier with 4 layers PN, and it has 3 junctions J1, J2, J3, and 3 terminals anode, cathode, gate taken out the P layer next to cathode. This is the schematic diagram, symbolic representation of SCR. And down here we have the two types of packaging for small power rating. Plastic case with metal tab is sufficient, whereas for industrial applications, heavy applications, large power application, we have the stud mounted fabrication where anode is threaded for bolting it to a heat sink, and this particular stud mounted structure is construction wise shown here in the left hand side diagram. As we can see, it is PN device, and gate terminal is welded here in the P layer for controlling the turning on of the SCR. Now, introduction to the thyristor. As we say, SCR silicon control rectifier is the first and foremost member of the most popular member of the thyristor family device. First, it was fabricated using a silicon based semiconductor and at Bell Laboratories and was called thyristor till 1963. The word thyristor is comprising of thyratron, which is a gas filled discharger device, and tube, and transistor. So these two words THYR of thyratron and ISTOR of transistor makes up the thyristor word, and it was adopted in 1963. In 1957, GC, the USA company, introduced its first prototype. Now let's see the basic structure of the SCR. As we already saw the structure, we saw that SCR is a 4-layer 3-junction unidirectional device with solid state PNPN device. It has 3 terminals, anode, cathode, gate, and anode we saw is threaded. Moreover, it's a 2-state device, is for efficient power control. 2 states, what are those states? The off state and the on state. In off state, it offers high impedance, high resistance, and in on state it has a small on resistance. It is turned on by applying a positive gate signal when anode is positive with respect to cathode, and for turning the SCR off, anode current has to be interrupted. There are two methods of turning off. One is bringing down the anode current below the holding current, and secondly by applying a reverse voltage across the SCR. Ratings: SCRs are available for 10 kVA, SIS 10 kVA, 3000 ampere, that will give the power handling capacity of 30 megavolt ampere. So that's a quite a large huge power that it can handle. That's why industrial applications make use of power device SCR. Here we see the basic structure of SCR with the junction J1, J2, J3 and the 4 layers P1, N1, P2, N2 with the cathode distributed and gate in the center, and this represents the different density. So we find equal density in P1 layer and N2 layer, whereas the middle two layers are lightly doped as compared to the P1 and N2 layers, and these layers have different thickness, 30 to 50 micrometer for the P1 layer, 50 to 100 for the N1 layer, and 30 to 100 micrometer for P2, and similarly 10 micrometer for N2. And the junction are behaving as diode or PN, the first diode, N1 P2 the second diode, and P2 N2 the third diode. So in normal biasing, anode is positive with respect to cathode, and in that condition diode D1 and D3 will be forward biased, whereas D2 will be reverse biased in the normal operation. So this is in the reverse bias mode. Now let's see the operating principle of thyristor by analyzing its two transistor model. The SCR can be represented with two transistors PNP and another NPN. So it can be splitted up as represented down here with two transistors and the gate terminal, anode and cathode here. So the base of one is the collector of another, base 2 collector of first, whereas the main current, anode current, is nothing but the emitter current of first transistor, and similarly cathode current is the emitter of the second transistor. IC is the collector current, I is the emitter current, and ICBO is the forward leakage current. Alpha will be the common base forward current gain, and relationship we know between IC and IB is IC is equal to beta times IB, where IB is the base current and beta is the common emitter forward current gain. Now for the transistor T1 and T2, we know the IC1 will be alpha 1 times the anode current emitter current plus ICBO, and similarly IC2 current will be alpha 2 IK plus ICBO2, and same relation for the collector current IC is equal to beta 2 times IB2. So applying KCL at this N point of the PNP transistor, we get the incoming current IA is equal to the IC2 plus IC1 or IC1 plus IC2, and substituting the value and solving it for anode current, we get alpha 2 Ig plus ICBO1 plus ICBO2 divided by 1 minus alpha 1 plus alpha 2. So if we are increasing this value alpha 1 and alpha 2, the forward current gain of the common base configuration, then it will be 1 minus 1 will be equal to 0. If it is equal to alpha 1 plus alpha 2 is exactly equal to 1, then denominator will be 0 and IA will result into infinity current that will damage the SCR. So it is not made exactly 1 but slightly less than 1, and in this way we can increase the anode current. Now the operation of the SCR can be understood with the VI characteristics. Here three modes of operation are there. Reverse blocking mode, where the SCR is offering high resistance, high impedance, as it is as the forward reverse bias, the anode is negative with respect to cathode, and therefore a reverse blocking leakage current is flowing, and as the breakover voltage is reached, a very high current will start running that may damage the SCR. So this part of operation is not desired, and the SCR remains in the off state behaving as open switch. Secondly, forward blocking mode, in which again there is increase in the voltage, and similarly the voltage gets built up across the device, and leakage current will be flowing till it reaches the breakover voltage. Once the breakover voltage is reached, till breakover voltage is reached, leakage current is there and it is in the off state, and the SCR is behaving as open switch. And third is the forward conduction mode, where it will be acting as closed switch. So when the breakover voltage is reached, it makes transition from off state to on state, and the voltage drop across the device reduces to in the range 1 to 2 volt, and that is the ohmic voltage drop across the 4 layers or the diodes in the layered structure diagram. And this voltage drop across the device goes on increasing with anode current. As the anode current increases, the voltage drop also increases. And this turning on or breakover voltage can be reached earlier if we are applying a small amount of gate current. So first case we are assuming as no gate current is applied. Second, when Ig1, a small positive gate current with respect to cathode is applied, and with anode positive. And as we go on increasing the gate current, the breakover voltage can be reached earlier, and thus we can control the phase at which the SCR will turn on. That's why it is called phase controlled or controlled rectifier. Now let's see what is the latching current and the holding current. The latching current is the minimum anode current required to maintain the SCR in the conduction state. This is the forward conduction state. So in order to maintain the SCR in the conduction state, the anode current has to be at least the latching current even when the gate signal has been removed, and this will be 2 to 3 times greater than the holding current, and it is related with the turn on of the SCR. Whereas holding current is also the minimum anode current required to hold the SCR in the on state. When this anode current is brought down below the holding current, then the device will go to turn off state. So below this holding current it turns off, and above this latching current it is in the forward conduction state. So these two are commonly asked in the board's paper. Now let's see the applications of the SCRs. There are many applications of the SCR: switching, rectification, regulation, protection. Here we can see the different circuits. The first circuit shows the SCR as a switch. Two SCRs are used that will turn on for the positive and the negative half cycle, and thus allowing current to flow through the load. So it can be used in choppers, inverters, DC circuit breaker, AC voltage stabilizers, pulse circuit, and home appliances for controlling the fan speed regulation, heating, temperature control. And industrial applications include the control of motor speed, battery charging, and power conversion. Here we can see the diagrams for the different application, half wave and so on. Full wave control, half wave requires only one SCR, whereas full wave requires two SCRs. Full wave bridge control will require 4 SCRs, rectifying both the positive and negative half, and 2 SCRs will be conducting at a time. Power voltage protection with the help of RS, CS, and the Zener diode we can provide